Welcome everybody very much to this webinar on the optimal layout of electric machines using MotorCAD and optiSLang. Today, your panelists are Unai Fernandez from Motor Design Limited in UK and myself, Markus Stockmeyer. Unai, do you want to introduce yourself?
Okay. Well, I am Unai Fernandez. I work as in the research area in Motor Design Limited, in some projects I'm developing the software MotorCAD.
Yeah, and I myself work at Dynado in the Service and Applied Research team. And yeah, so first, this is our outline for today. We'll have a few more words on both our companies, Motor Design Limited and Dynado, and the software products we produce. So in the intro block, there are a few more words, and then there is the main content, and it's on what's it all about, designing electric machines, what are the challenges, how can you design a better or a worse motor, and second block is about what is design variation with optiSLang all about, design of experiments, sensitivity study. In optiSLang, by sensitivity study, we always mean response surface-based sensitivity analysis or meta-model-based sensitivity analysis. What's the advantages, just as a few bullet points. And then we're going to look at the most important things tonight, and that's the connection between MotorCAD and optiSLang. So you have MotorCAD, which is a fast solver for electromagnetics and thermal behavior of electric machines or performance maps, and optiSLang can drive a variation study and can analyze the statistics of variation studies and can apply the meta-model-based sensitivity analysis or can run optimizers. So just as the two central points, the two takeaways I tell you already right here. It's the integrated workflow. So this is how a system looks like when optiSLang calls up MotorCAD. So I just can show you this right here. This is a parametric system, and this is one. So we can either drive MotorCAD with a Python script over the so-called ActiveX connection. We load MotorCAD, we load a file and run it, and you can start with a script we supply to you and then extend it, and in the script you completely control everything. Or this custom integration system is built with a custom integration solver wizard. So here is a custom integration solver wizard where we will go through in a second. So this is a convenience system, and you just have to drag and drop parameters like this. And when you run it, it pulls up MotorCAD. So these are the two important points today. The integration of the two software, of the two programs, and once you have it set up, once you can conduct optiSLang-driven design variation studies and optimizations and robustness evaluations with optiSLang, and once the two pieces of software are integrated, you can explore your design space much more efficiently. So you're designing an electric machine, you have lots of choices, you have lots of parameters, there are lots of degrees of freedom of where you go, what's your optimal motor, and therefore this should be the main message. With the two tools in connection, you have the best leverage to really tackle, to really explore efficiently the design space you have, to leverage your design degrees of freedom. Okay, so now let's start with the main content, electric machine design, and optiSLang and MotorCAD, the connection. But first, the little intro slides. So here I would pass the ball over to Unai.
Okay, thank you, Markus.
Here you go.
Okay. Can you see the screen?
I can see it perfectly.
Okay, thank you. So Motor Design Limited was founded in 1998 by Dave Staton. He started developing MotorCAD software for electric motor designs, and it was solving analytical thermal models based on lambda parameter thermal models. In the company, we have a high level of customer support, so we work very close to customers, and every feedback is taken into account to implement new features into the model. And we work in many projects. Some of them are funded research projects in the UK or Europe. And in these projects and also consultancy projects that we work, we use innovative solutions that are implemented into the software. So, and we are also a strategic partnership with ANSYS. So in this example is optiSLang, the link that we have with optiSLang we are developing together. MotorCAD is distributed worldwide, and we have customers in different industries like automotive, aerospace, industrial applications, traction, renewable energies, or different universities. So we can develop new models, new methods to estimate things, and we can implement into the software. MotorCAD is a software which is based on templates. So we can design many different topologies of machines. So after choosing the topology, which could be, for example, brushless permanent machines, inner or outer rotor, or induction machines, synchronous reluctance or switch reluctance machines, after choosing the topology, we need to define the dimensions of the different parts of the machine, like magnets or the lamination, the winding, and everything is parameterized from the interface. So it can be in few minutes. The models can be generated for both the electromagnetic or the thermal models. MotorCAD has mainly three modules, which are EMAC, Thermal, and Lab. Thermal was the first one developed by Motor Design. As I said, is using analytical models based on Lambert parameters thermal models. In the EMAC module, we use the same interface, so all the geometries are parameterized, but we use a 2D FEA solver to calculate flux linkage and losses in the machine. And then we have a third module, which is Lab, which is an analytical tool that is using FEA simulations from EMAC to build 3D maps and use interpolation to estimate any operating point in the overall performance of the machine, different currents, different speeds. So here is some examples of parameterized geometries that we can model in MotorCAD for the lamination or the windings, and different analytical tools that we can use to analyze the winding, for example. We use a 2D FEA solver, which is very fast, and in few seconds you can run transient simulations with torque calculation and losses, and all the losses are estimated from the FEA results. The thermal model in MotorCAD is based in Lambert parameter thermal models, as you can see in the picture. This is an actual representation of the machine with the shaft at the bottom, which is connected to the rotor, the magnets, the stator, the winding, and the housing at the top. Each node represents parts of the machine with the same temperature, and each node has a thermal capacitance, which depends on the material properties and the dimensions. And all the nodes are connected with thermal resistances, which can represent conduction inside bodies, conduction between different parts, or can be convection, with natural or forced convection, and radiation. If any correlation needs to be used for the convection or radiation, MotorCAD will use the operating point and different correlations from the literature to estimate the thermal resistances automatically. This way we can run thermal transients in seconds to predict the temperatures with different duty cycles, for example. And the third module I said, which is Lab, is an analytical tool that runs FEA calculations to build 3D maps of flux linkage or losses of different parts of the machine, like the lamination or the magnet in different parts. So by doing sensitivity analysis of current and phase advance angle, we can interpolate the operating point at any speed and also any current. This interpolation allows us to calculate efficiency maps in seconds after building the model, which normally takes 5–10 minutes. So we can calculate in seconds efficiency maps, or we can calculate duty cycles by specifying the torque and the speed versus time. We can estimate the required current and phase advance for each operating point, and then calculate the losses that will happen, and automatically export the duty cycle with the different loss values into a thermal model to run the thermal simulation in seconds again. Here's some example of the Toyota Prius model that Marcus will use later for the optimization. So here we can compare the efficiency map calculated by MotorCAD is compared to the experimental data obtained in lab tests. Another example is the Nissan Leaf motor. And here we will compare the efficiency maps calculated by the FEA and also the thermal tests running in the lab versus MotorCAD thermal simulations. And this is a quick overview of the software MotorCAD. You want, Marcus?
Okay, yeah, thanks a lot. Okay. So let's switch to the second part of the introduction. Okay, just 2 slides on the company, Dynado, which was founded in 2001, steadily grew to more than 60 employees now, 2 locations, Weimar and Vienna. Also, there is a steady growth of the customer base, including technology companies from all across the world, Europe, US, Asia. The 3 main software products of our company are optiSLang, that's this symbol here, statistics from structure, there will be one more word on the next slide, and Multiphysics. Developing the software, we have a steady input from our consulting department. So the consulting department is one half of the company. They are working on real-world projects, and they give us the feedback, they give us the critique, hey, the math is there, but I cannot use it, it crashes, or it's impractical. So we have a steady inflow of critique and feedback from you, from the customers, and also from the consulting team, and therefore there is also a quick development cycle. And what does it mean, real-world capability, for example, handle failed designs, handle lots of parameters, handle noise, things like that. So this is how we develop optiSLang, the software you use for driving design variations and analyzing how the outputs are varying, sensitivity study, metamodel-based sensitivity study. And if you use the math for the scalar responses in optiSLang and you generalize it to field outputs, this means you take into account if 2 outputs are correlated. For example, the thickness here is correlated to the thickness here and correlated to the thickness here. So you can take into account correlations across space, and that's more math based on mode decomposition, and that's our second software product, statistics on structure. Then there is Multiplas, the material library, and Multiplas is just short for multiple plasticity, and this means plasticity in space, or plasticity vectors, plasticity planes. And optiSLang is one piece of software, but you can look at it from 2 sides, and you can look at it from the original graphical user interface, or you can look at the same software from Workbench plugin. So for Workbench, there is a plugin, and you can use optiSLang system, sensitivity, robustness, optimization inside Workbench. So real-world capability means multiphysics, nonlinearity, lots of dimensions, and we need to deal with failed designs. We need to deal with a license failure, computer is crashing, I want to have on the next morning, I don't want to start over, I want to have a save point. So when I see a window popping up, did you want to say something? There is an annotation request. Which keeps popping up. Yep, let's move on here. Graphical user interface means we can use the scenery for graphical programming. This means you can set up basic workflows with inputs, solver call, output, or the solver call can be Python, Excel, any finite element tool which can deal with inputs or outputs, or any finite element tool which we can, or any simulation tool or solver which we can address over the COM interface. So from simple workflows to complicated workflows, nested, linear, branched, everything is possible. So today we are going to look at the integration of Motor-CAD, and there are, basically, it's ActiveX is the interface. ActiveX is how the two pieces of software communicate, and here are two setups, which I will just demonstrate to you in a second. One last word about the purposes of driving a design variation study, and particularly driving it with optiSLang. So you can tweak the settings of a solver because you aim for the solver being capable of representing reality. As soon as the solver represents the real physics you're interested in, then you can use it, as long as the solver is not calibrated. Some solvers need calibration. Sometimes it's just a material constant. Sometimes it's more state parameters of a solver. So that's a subclass of optimization. Generally, we have the three topics of sensitivity study, optimization, and robustness evaluation. So here, sensitivity studies means examining how outputs react when I change inputs. Is one parameter influencing an output? Do I need the change of two parameters to influence an output? That's coupling. Is it reacting linearly? Is it reacting non-linearly? And you gain design understanding. You can get a response surface which represents the response Y depending on many inputs X. After the sensitivity analysis, you can devise a targeted, efficient optimization strategy. You can run optimizing algorithms on the simulation. You can run optimization algorithms on a meta model, and then you save on the simulation budget. Generally, if you leverage the knowledge from the sensitivity study, your optimization problem will be much, much, much slimmer. So always first the sensitivity study for gaining knowledge, and then a targeted, efficient optimization strategy instead of just a black box algorithm for a black box problem. For example, you optimize the body in white of the car. For example, you can optimize a bridge. That's about structural mechanics. If it becomes leaner and leaner and leaner, maybe you optimize for two different load cases, and in the end you have three more wind load cases or crash load cases, and then you examine, and then you find out, oh, it got too lean. So is it still stable under scattering loads? Is it still stable under scattering material thicknesses? Is it still stable under scattering material properties? All that, scattering tolerances. So this is, you can apply a design variation study, and you can apply the dedicated algorithms from optiSLang to examine your simulated system under the viewpoint of, is it robust? Robustness, sampling / reliability proof. That's the topics here. And I have some slides here which I just leave in, and you will find them in the PDF later. So we have scratched all that, so I just jump over that. And now let's start with the real content of today. So electric machine design, what's it all about? Perhaps we can say it's about topology, it's about allocation of space, it's about shape. So topology, how many slots, what winding allocation means, how much space for copper, how much space for iron, how much for magnets, and shape means the shape of the slots, the shape of the T, for example, to increase the performance, to increase perhaps for example, NVH properties. So the first question is always, what type of machine are you going to use? So here I just assembled a few snapshots of the templates in MotorCAD. So you see the green magnets here, surface mounted, embedded magnets here, an induction motor, reluctance, use reluctance for torque generation, use a coil for creating the north and south poles. And even if you decide on one type, you still have to decide on the number of poles, the number of slots. For example, how many magnet layers have we here? And for 3 magnet layers, you have 3 angles, 3 widths, 3 thicknesses, and then you have all these geometry details, which may all affect the performance of the machine. And that's why you go through a series of topology decisions and then geometry tuning decisions. And what's the physical background? Here we have the magnets. The magnets generate the magnetic field. Here we see the field distribution if the coils themselves do not create any field. So we can see just the field from the magnets, and you see field lines are shortcutting here, and field lines are going all around to close from the, for example, the North Pole in front to close back to the South Pole in the back. And if field lines shortcut, they don't contribute to torque generation. If the field lines go around the winding, then if the coils generate their own field, then we can generate torque. And so this means this bridge should really become thin, because the flux leakage here, the shortcut paths, they are undesired. But if it is infinitesimally thin, then of course it breaks. This chunk will break off due to centrifugal forces. So you can see a classic trade-off here, a classic design conflict. From the EM, from the electromagnetic perspective, you would like to minimize this bridge. From the mechanical perspective, you would like to maximize this bridge, so you have to find a compromise. Just like that, you have to find compromises between having iron here for conducting the magnetic field lines, or having copper here for having the largest possible cross-section to get the current through without ohmic losses. So that's the next trade-off. Then there are trade-offs in terms of the thermal behavior. There are trade-offs in terms of the forces which excite vibration, noise, vibration, harshness. And by choosing the right topology, and once you have the topology, by choosing the right angles, thicknesses, the right air pockets here, you can control the field lines, you can control how the motor generates forces, you can control how the motor generates torque, how efficient it is, how much losses there are in the iron, in the copper. And this is what you aim at when you conduct parametric studies and when you conduct optimization trials, optimization runs on such a simulation. And because MotorCAD simulates it all so fast, you can do lots of experiments. You can try lots of alternatives. You can try out lots of load cases. So first we have topology, we have allocation of space, magnets, winding, iron, and we have shape details shaping the different parts to increase torque, power, efficiency, performance, to increase NVH performance. Not to forget, there is a third dimension, there are different working points. You can apply different circuitry, different types of circuits for the electrical drive. You can apply different cooling concepts. And with MotorCAD, it's really fast, and you can try all these alternatives out. And with optiSLang, you can use efficient sensitivity studies and optimizations to really optimize each case and compare optimized cases. And like this, you can leverage the design space. You have lots of decisions to make. You have lots of design space. You have lots of variables. So here today, we show you how you can integrate MotorCAD and optiSLang in order to be able to leverage the design space. So Una, we went through your case study slides, right?
Yes.
Okay, then let's, before we look at that theory chunk, let's then just have a look at the system, at an exemplary system. So here are the two ways of integrating optiSLang, integrating MotorCAD into optiSLang. So I just show you how to set up such a system. There is a convenience solution. It's the custom wizard, which sets up a custom integration. These scripts are not within the installation, but you can just email us and then we send you the scripts and you can try it out. So if I point the wizard to a file, a MotorCAD file, then the Python scripts analyze the file and you will get such a system in a second. Then you can decide from this menu, are we aiming at producing a performance map in lab? It takes a few minutes, so let's go with the electromagnetic model here. It takes a few seconds. There are no parameters as of now, so let's register some parameters. I just take some parameters. So now we have 3 parameters, upper and lower bounds. You can switch to integer string, you can switch to discrete. For example, you can modify upper and lower bounds like this. And there are already some outputs. For example, torque, eta, losses. Let's register that. And now let's run the system, and you will see how optiSLang pulls up MotorCAD. And now MotorCAD will load the file which has been associated through this wizard. And we can switch to the eMagnetics tab in order to watch MotorCAD at work. While it's working, I can show you we have the result designs tab. This is the design which is calculating at the moment, the 3 input parameters but no responses. And now let's watch the finish of the work. Now the system turned green, it ran successfully, and we see the successful status here, and we see that now we have the registered responses. So you can copy that system, you can change the values here, and then you can conduct a manual design variation study. Of course, that is not what's intended. What's intended is to, for example, conduct a sensitivity study. Here we can revise the parameterization. We might already define some goals, even though they're only necessary for optimizers and not for sensitivity studies. Okay, I need a value, of course. And this is how the wizard takes a system and takes this system as a template to generate a sensitivity system, and it has post-processing and one post-processing node for the meta model generation. So you can tell the system conduct 100 simulations or 200 simulations and what's this? It's how to scan the space. What is the design of experiments? How should we distribute the points throughout space? And then you can conduct a sensitivity study for examining what different types of machines, what different types of performances can I find within the space defined here. Okay. Maybe one last word at this is similar. So this second type just has a Python script, and you in this Python script you can control completely in which sequence MotorCAD does what. So for example, first load the file, modify the parameters, and here where's the important line? The important line is here magnetic calculation, and later on, for example, the thermal analysis. So if you work this way with a script, you can define everything and control everything. Okay, let's go back to the slides, because now if you conduct a parameter variation study, what's the specialty of optiSLang if you use it? What's the purpose of a meta-model-based sensitivity analysis? So we have inputs X, our system produces outputs Y, and when we are scattering design points with different combinations of inputs, then the question is there a tendency? If I'm varying one parameter, how does the system react? Is there a decreasing tendency, or is it just scattering? So here I don't know how the response reacts to the change of the input Y, but you just changed the situation very slightly. The data set barely changed, and here you see a clear tendency. So the question is how to detect that? What algorithmic tools, what math tools can you use to detect system dependencies? And such a linear regression, this linear model, would be a very simple model for representing the system behavior. If X grows, Y decreases. That's modeled with this with this linear function. But what happens if the response is nonlinear? What happens if X has more effects, X1, if another parameter, X3 or X5 is changed at the same time? And if both don't change at the same time, then the effect is not as big. So parameter interactions, nonlinearity, more dimensions, that's the question. So is the system sensitive to a given parameter? Are parameters interacting? And how do we get to this information? And that's the questions you can answer with a response surface-based sensitivity analysis. Okay, so we have been looking at the integration. So if you have your solver integrated, we can conduct the design variation study. And so let's look at the very, very simple example. For example, I'm varying just one-dimensionally one parameter. So the parameterization is here. All the parameters are constant for this IPM machine, except the slot depth. And if you look at the post-processing, it was just 5 designs. You can see the input slot depth. You can see which output are we looking at. For example, the copper area. If the slot has more depth, the copper cross-section grows. The copper losses, the stator losses grow substantially. The rotor losses are not so much affected, and I have something non-linear for the total losses. And if we look at it in 2D, for example, slot depth and slot width, you can see, for example, how the copper cross-section grows with slot depth, how the copper cross-section grows when the teeth become slimmer, and that's quite logic. And if you look at a quantity like the efficiency, you can see here the nonlinear response. And it's just 2D. In this two-dimensional world, we can use these 16 design points, 4 by 4. We can use this full factorial scheme to get a pretty good feeling of how the system reacts, even how the system reacts non-linearly. But how about many dimensions? How does it look like if I'm varying many parameters? So for one-dimensional case, for the one-dimensional case or the two-dimensional case, if you look at the meta model, is just an interpolation. If the curve goes through the points, that's okay. If the response surface goes through the points, that's okay. If I want to maximize the efficiency eta, well, this is the best point. So here I have the best point. So the best point is simply ticking, and then you know. So the interpolation is the best fit, and you can pick your best design. But how about that? You have 10 parameters, you're varying, you have lots of responses, For example, you want to maximize the efficiency eta, you want to maximize the torque. The maximum for eta is here, but the maximum for torque is where eta is low. So where is the best torque you can achieve with if you accept eta to go as low as 75%? What's the torque you can get if you accept eta going down to 0.7? Then you're examining a 10-dimensional space, and you can leverage the meta model gained with the sensitivity analysis to do that. And it gets particularly interesting if you have a quantity which reacts with more nonlinearity. For example, torque ripples here. That was an analysis of an old permanent magnet brush commutated motor. Here there is a lot of nonlinearity. There are local minima of torque ripples if you're varying the magnet coverage. And then it gets really interesting if you have local optima and if you have lots of responses, lots of non-linearity. And with optiSLang, you get nonlinear meta models, and you get the sensitivity study, and one result is the coefficient of prognosis, which gives you a conservative measure of the meta model quality, which gives you a reliable measure of how much, what quantity, what percentage, what fraction of the physics has been captured in the meta model. And if you have that captured, then you can use it to get ahead in your optimization problem. So slides here for future reference. If you look at the PDF slides later, the meta model of optimal prognosis is the winner of a competition. The competition is really neutral. There are lots of meta models, some with more, some with less input parameters, and the best one is winning by forecast. And forecasting, prognosis, prediction, how does it work? It works if you divide the points into sets of support points and sets of testing points. So this means cross-validation on sets of test points. And that's how the meta model of optimal prognosis is distilled by a competition. In terms of optimization, we have optimization algorithms which you can apply directly to the simulation, or you can run them on the meta model, slim, efficient gradient followers, or powerful global optimizers. Here the idea is just to go downhill. Here the idea is try out lots of parameter combinations, use survival of the fittest as the principle, use operators for selection, pressure, recombination, mutation, use other inspirations from, for example, thermodynamics and simulated annealing. And here, slim and efficient go downhill, but if there are local minima, well, you end up either here or here. They are powerful for global search, but you might need several hundred designs. And therefore, in optiSLang, the default algorithm, the algorithm which performs really well on lots of cases, the algorithm which is a perfect compromise between efficiency and being robust against local minima is the so-called adaptive response surface method. And now we can look at applying algorithms to this IPM model. And in the exemplary study for today, I just set this here. It's just one working point, 3000 RPM, 50 ampere, one phase advance angle. But I conducted both the EM simulation. The losses are transferred to the thermal model, so the temperatures are depending on how much losses there are in the copper, how much saturation and losses there is in the iron, and so on. We had already a look at 2D meta models, which are not so interesting, and it's just a glance, and you know it's good or not good. And here it's interesting. What can we do with a 10-dimensional meta model? Well, we can use it for understanding the system behavior, for learning about the machine, and then we can use it for optimization. So let's have a look at that result. The 10-dimensional meta model. So here, it's an advanced pattern hypercube sampling, 200 designs, and there are 10 parameters and no parameter is constant. And the result designs, you can see here all the input combinations, and under the dark gray shading, all the outputs. And we're collecting scalar outputs, but also signal outputs, for example, the torque curves of the different designs. And this is a result. So, for example, the efficiency, slot depth, and tooth width are still the two most important parameters. So you can see that here. Slot depth and tooth width are the two parameters which have the most impact. And so if you change slot depth and tooth width, for example, here, you have a lot of change in the response. But of course, the picture doesn't change because tooth width, I'm just going back and forth in the picture. Slot depth, I'm just going from left to the right. But let's take the third parameter, web thickness. This is the third parameter of the meta model. And you can see how the surface changes. The least important, magnet thickness, it still has a visible effect. And you can still tune it in a way to maximize the efficiency or to minimize the efficiency. So are the points off? Is the meta model not going through the points? No, it's just a 10-dimensional, or here it's a 7-dimensional space. And the meta model maybe captures all the points. Well, how well it captures the responses is given by the coefficient of prognosis. So here, 96% of the variation of this response has been captured in the meta model. And the coefficient of prognosis is it's not a closeness of fit, it's based on cross-validation, on independent test points. And how the cross-validation, how the deltas look like, so here are the values from the data on the x-axis and the values from the meta model for the independent cross-validations on the y-axis. So this gives you a good estimation of how far the points are off. Or you can examine for one point, for example, I choose this point, I use this point's parameter settings, and you see all the sliders adjust, and you can see how far the meta model is from that point. Okay, so now we can maximize eta while keeping a constraint, for example, on the torque. The torque should not drop lower than something. Or we can maximize the torque while the efficiency doesn't drop below 97.4, for example. Let's look at the torque just to show one more. Outputs here lower. That was the third one. Shift torque here. Okay, this is, for example, the meta model for the torque. And if I have less magnet width, I have lower torque. If I have more size for the magnets, I get more torque. This is plausible. So you can always do these kinds of plausibility checks. Okay. What comes next? I can use this meta model to set up an optimizer. For example, like this. I want to maximize the torque while abiding to a constraint for eta. And this optimizer now runs on the meta model. Or I can run an optimization with it on the simulation directly. I can import the criteria I just defined, so I don't have to type in expressions again. So by contrast, this optimizer runs calling Motor-CAD. And I conducted an optimization. I just stopped it this morning. And this optimization was the working point at high torque, high current. And it had the goal to minimize the torque ripples. So let's look at the torque curves. So initially, there are designs which have higher torque ripples, or I hope you can see the signals very well. For example, this curve has not so high torque ripples, but it has a torque of just 200. And therefore it fails, the torque should not drop below 308. It fails this constraint, and therefore as constraints fail in design, it's a red dot. A green dot fulfills constraints. And the best design is this one, and you can see how the optimizer minimized the torque ripples while still keeping the torque. So you can see torque above 308. You can see what else was there? Yeah, I would have to look what other constraint I had. So this is a result of an optimizer running on MotorCAD, and the optimizer was working on optimizing the goal I give it. I will just close a few post-processings in order not to overburden my graphics card, which is busy with recording. And I guess this is already the right one. I'm not sure whether it is the right one. So I will just put these new optimizers out of the way. So here, the meta model was used for an optimizer. And this optimizer is an evolutionary algorithm. It's a powerful global searcher. It has the goal to minimize, here's minimization, minimize the winding temperature. And it has three constraints: keep the torque above 50 Newton meters, keep the magnet cross-section below this value, and keep the efficiency above this value. And it went through a couple of designs, and it found an optimal point, and it found this optimal point on the meta model. So you can see here the meta model solver, not MotorCAD called with Python. And when I optimize on the meta model, I want to check. So here is the best design is checked by calling MotorCAD again. So I have 200 designs for the sensitivity study and the meta model, and then one more design. And this is the results. So these are the points which violated one of the three constraints. And these are the points which fulfilled the constraints. And the objective is the winding temperature, and you can see it was minimized here. And now if I look into this here, you can see for each response here, you can also click on the response, and you can see how the plot updates. For each response, for example, the torque here, you can see on the meta model, this was the optimized value, and this is the check on running MotorCAD again. So there's a little offset because the meta model is always just an approximation. And I switched to the slides because I want to show you the comparison of three different optimization runs. And this is just to show that you can we saw already you can run an optimizer directly on the simulation, but if you run an optimizer on the meta model, you can ask lots of what-if questions and get answers in minutes. And if you rely purely on simulation, you will get answers only within hours or the next day. So if the constraint is higher, for example, 60 Newton meter for the torque constraint, then the optimizer has a harder time finding good designs. First, it creates lots of random infeasible designs, violating the constraints, and only slowly the fraction of constraint fulfilling designs grows, and then it is optimizing the goal. And here we go through, so this is the optimized design, the reference design, and the optimized design. So for this single working point optimization, if you want more torque and if you want a better efficiency, it's minimizing, for example, the bridge, and we know that there is a trade-off, there is a conflict with mechanical boundary conditions. We don't want to make this motor unstable, but we know why the optimizer is doing this. So you will find that in the slides. But now it's about this here. We can ask different what-if questions if we just copy that workflow and run the optimizer under different conditions. So here, the condition, the easiest condition, 50 Newton meters, is the constraint for the torque. And how does it change if we increase that, if we make this condition more challenging? So 55 Newton meter, more red points. 60 Newton meter now, you can see the optimizer has a harder time finding the first feasible designs. Only one feasible design in the first 500 designs, and then survival of the fittest slowly repairs the violated constraints, and once we have a good fraction, then we really optimize the goal. And you can see here at this constraint, 65 Newton meters, there are barely any feasible designs, but the optimizer finds it. The optimizer here needs 3,000, almost, well, 2,500 designs to explore this 10-dimensional space, but it finds a corner where there are designs which fulfill all these challenging constraints. In a real simulation with a time-consuming finite element solver, this really hurts. But if it's a meta model and the meta model is just a function call, then I can try that out. And if I find that I can find a solution here, well, then I can, with the best design I can get, with that I can go back to the simulation. And like this, you can be more efficient. 200 designs for the meta model. You can ask all these what-if questions. You can find out what's possible at all, what's not possible, and then you can go back and then you have a much slimmer optimization problem if you go back to the simulation. So as one last slide on this topic here, on this optimization case study operator fund. So that means let's have the optimizer fulfill two goals: greater torque and lower temperature. That was the okay, here it yeah, so I forgot to tell one thing. So the goal is to minimize the temperature while we have these constraints here. So with the easy constraints, we get a very cool motor at 90 Celsius. Here we have 100 Celsius for the best solution found, which is here. We have 108-ish, and here 120 Celsius with 65 Newton meters. And here you see it all at once. With a limit of 50 for the torque, we get 90 degrees. If we want 65 degrees, well, with this implemented constant cooling setup, you have to accept 115 or 120 as the resulting temperature resulting from the increased losses. So you can run lots of single objective optimizers, or you can run here a couple thousand designs on the meta model. On the meta model, we don't care. And then we know from the physics captured in the meta model, from the nonlinear system behavior captured in the meta model, we can know that at a glance. We can explore this trade-off. And then you can know what's feasible, and then you can go back to the simulation. You can color the points in the optiSLang post-processing, so green color for a few points over here, red color here, cyan color over here. Where are these designs coming from? Let's go back into the space of the input parameters. So in the light gray, so from here to the left on the light gray background, we have the input parameters, and you can see that the right end of the Pareto front comes from here, and the left end of the Pareto front comes from here. So large tooth widths in comparison to small tooth widths. And you can see the three clusters are really separated on the tooth width axis, but you can see the three clusters are intermingling on the spacer bore axis. And here it's really interesting. For web thickness, we have the left edge of the Pareto front really separated, but the red and blue, they are intermingling. So why is that? Why can I get the hot motor, so the high torque or the medium torque, I can get both in this range for web thickness? Why is that? What's the reason for it? So you get, this can trigger you to ask interesting questions very quickly. So I put this here, get the value from the simulation, because you get the captured physics in the meta model. You can explore the meta model by hand, looking at the post-processing. You can send optimizers exploring the space. What designs have I at my hand? What's feasible in this design space? Do I have to shift to the space? What's feasible in the other space? So, and why is it? What causes higher temperature? What causes higher torque? What's the trade-off? If I have higher torque, where do I have to take the drawbacks? And where does it come from? How are the other parameters interacting with it? What's which thickness to tell here? You get very quickly to the interesting questions. And so there are two extreme cases for using simulation. So either you use simulation and an optimization algorithm to be lazy. So you just set up the simulation, set up the optimizer algorithm, and you wait for a weekend, and then you have the optimized motor. And if you don't look at what's happening, if you don't ask yourself why the motor is optimized, then you don't learn anything. So if you have a good result after one weekend, and for one project, you cannot ensure that you have a good result next time because you didn't expand your competences. The other extreme cases is you go through one simulation, you change something, you look at the field lines, you look at the torque, you look at the details, you look at the mesh, you look at everything you can visualize in the simulation, and you can find out, wow, the torque ripples are really coming from here. Look at the field lines here, how they distributed. I can explain exactly where the torque ripples come from here, and then somebody asks, okay, so what can you do against it? Oh, well, that's a good question. Well, we could change something here. We could also change something here that has this drawback, that has this drawback. Yeah, so what are we doing? So here you can explore the design space. You can find your good designs, your bad designs. You can get to the causality of the problems, and you can find these corners of the design space bring good solutions. And you do the same budget of simulation, or you run more simulations in shorter time, and you expand your knowledge, and you expand your competences, and next time you know more, and you know which optimization strategy you should apply. You know about your trade-offs, you know about the goal conflicts, and you know about how to set up the optimizer. So get the value from simulation. If you have the algorithms, if you have the algorithms, the power, the maths, if you have the visualization, if you take out what you have at hand, if you do data mining in the design variation, then you can get to the knowledge and you can expand your competences. So if you have MotorCAD and optiSLang coupled, you can learn and you can leverage the knowledge you get, and you can leverage the design degrees of freedom you have when you create a motor, when you design a motor, when you set up the layout, and then when you optimize it. You have state-of-the-art electric machine simulation and really fast with MotorCAD. MotorCAD allows you to go to compare, to try all the alternatives. You can optimize one alternative, optimize a second, a third, a fourth alternative, and compare the optimized ones. You have state-of-the-art sensitivity analysis, meta-model-based sensitivity analysis, and robustness/reliability algorithms with optiSLang. Graphical programming, workflows comes on top. You create a workflow, you create a template, and you use the workflow next time. So this is the spectrum of use cases. You look at the data, you look at the visualization, you ask yourself what causes the effects, and you learn about the causality dependencies. And with that, you become knowledgeable about devising a targeted, efficient optimizer. You can run a black box optimizer on a black box problem. You spend 500 or 5,000 designs, and you have something, and it's optimized, but is there more optimization potential? You might know, you might not know. If you know what you're doing, then you know this setup works, and if this setup works, you can apply it next time for the next project. You can email it, and you can give this setup to the next colleague of yours. So you cast your competence into workflows. That's and everything in between here is feasible. And so at Motor Design Limited in Ellesmere and at Dynado in Weimar, we are doing the best to program the pieces of software which give you that power to explore the design space, which give you that power to leverage the degrees of freedom you have when you design a motor. So as a quick summary, MotorCAD, slim, fast, analytical models, a thermal system simulation, a 3D system. Cooling is different from the back, from the front. You can insert nodes. You can calibrate with your own heat transfer coefficients. You have lots of predefined machines. It's everything fully parameterized, and it's so fast. You can examine different types. You can examine different load cases. You can examine different circuitry driving the motor, so you avoid the single load case myopia. You can optimize for one load case, or you can optimize for different points on a performance map, or for the whole performance map. You can automate it. and then you can power up with optiSLang. You can vary 10 parameters. You can also go through a design variation study with 20 or 30 parameters. And the meta-model-based sensitivity analysis tells you these are the 3, 4, 5, 6, 7 most important parameters for this quantity. And 5 other parameters are influencing the other quantity. And here you have a good solution. So you can leverage the meta-model, you can get all the knowledge, you can deepen your system understanding, you can get the insights on the causality, on the physics, and then you can devise an efficient optimization strategy, and you can templatize it, and you can use that optimization workflow the next time. Yes, and of course, we have seen that you can ask what-if questions on the meta-model. For example, can I get a design giving me 70 Newton meter? Probably not. I can get one at 55 or 65, and then I can get different temperatures. So that's what-if questions asked on the meta-model. Okay, so all this enables you to deal with the design degrees of freedom you have. With that, the main content is finished, and with this, we should now really look at your questions and answers. And Unai, if you have anything to remark.
No, I think your description has been very complete.
Oh, okay, and then we should look at the questions. Did you already look at it? Were there some questions? I will pull up the windows again.
Yeah, I have. Did you read?
Yeah, I have the windows here. I just adjusted the size and using the second screen. They always switch to the first screen where okay, now it works. Okay. Hi. Okay. Yeah. Yeah, so I think we will stick here for a couple more minutes and answer these technical detail questions for the purpose of finishing the video recording, which we want to distribute publicly to everybody. I would like to finish here, so I would like to thank you everyone for staying on board or for watching the video, and please. Feel free to ask any questions. You can get trial licenses. You can get the scripts if you want to try out MotorCAD. You can get models. You can get assistance. You can get training. So here are email addresses and web addresses: dynado.de or motor-design.com. So you know the contacts. You will receive an email with the PDFs and links for downloading the PDFs and links for downloading the video. And with this, I thank you very much and say goodbye. And Unai?
Okay, thank you very much, Marcus.
Okay. Yeah. And thank you, Unai, for joining for this webinar. I think it was very good very good experience to worked with MotorCAD and set this up, the case studies, and I learned a lot. Okay, so thanks, and I will stop the recording here.